Okay. Hello, everyone. Welcome back to the second day of our workshop. So today we start with Lucile Devin from Université du Littoral Côte. She's going to speak on low-line zeros in families related to CM elliptic curves. Please,
Obrigada. Well, thank you very much for the introduction and for inviting me to be here. I'm very grateful to the organizer for giving me this opportunity to cross the equator for the first time and visit this very nice country, visit this very nice place, and get to meet the Brazilian community, which is very nice. I'm very happy to meet you, so thank you. And yeah, I'm going to talk about some recent results that I have with Chantal David and Ezra Waxman on low-lying zeros in families related to CM elliptic curves. And, well, okay, the plan is to first discuss why we're interested in those questions, and maybe we'll have the result in the end. So yeah, the first question we're interested in this talk, and a lot of number theorists are interested in my opinion, is to find where the zeros of zeta, let's say in general L functions, where the zeros of the L function. So, well, you know, they're on the line real part is equal to 1/2 and whatever. I'm not going to prove that today. And so I'm going to simplify the question a bit because, yeah, that's a bit too hard to say that. So maybe the question I'm interested in today is there a zero at 1/2 for the L function, which is related to rank for elliptic curves, for example, like by Birch and Swinnerton-Dyer conjecture. And, well, that's already a difficult question. So I want to know if, in general, there is a zero or not at 1/2 for the L function. And that's actually even a too difficult question for me today. So I'm going to ask a different question, which is, if I give you a box of, say, imaginary part between minus 20, let's say positive, 0 and 20, and real part between 0 and 1, how many zeros are there in this box? Okay, so in this box, there is definitely the 0 at 1/2. And there is a bit more, but that's like a good approximation of what is the multiplicity of the 0 at 1/2, or a good upper bound for the multiplicity of the 0 at 1/2. Because already for zeta, there is only 1 0 in this box. So yeah, good upper bound for the 0 at 1/2. And for this L function, well, there is a bit more, but I would be happy to be able to say that there is only 1 0. So I'm going to change the normalization. Yeah, so let me start again. So yeah, so there is approximatively, if you count the zeros by the Riemann-von Mankel formula, there is approximately 20 over times log 20 of C, where C is the conductor, which is the good constant associated to the L function. Imagine if you're looking at, well, if you're looking at zeta, the C is 1. If you're looking at Dirichlet L function, then the C is the modulus of the character, let's say primitive character you're looking at. And then if you're looking at fancier L function, then this is also some good constant associated to the arithmetic object underlying the L function. So, well, so there is this C, and so I'm going to, instead of counting 0 up to imaginary part equal to 20, I'm going to count 0 up to imaginary part 20 over log C, so that there is about the same number of zeros when I'm approximately so that I can compare the number of zeros between the L function. Okay, I want to don't divide by zeros. I'm just going to put a 20c here. Okay, so that's the thing we want to study. How many zeros are there in such box? And well, as I said, what I wanted to say in the beginning was just, is there a zero at 1/2? And since studying only one L function is difficult, I'm going to study that question in a family of L function, where family is, for now, something very vague, which is just, I'm looking at L functions that look like each other. For example, L function associated to direct-line characters, or L function associated to quadratic direct-line characters, or L function associated to elliptic curves, or whatever is your favorite L function. And if you don't like L function, zeta at different values of t, say. I hope everybody likes zeta, if not everybody likes L function. Yeah, so, and then, so I have this C that is, okay, that's not what I wanted to do. Yeah, that's what I wanted to do. I have the C that is the conductor associated to my L function. I'm going to index the L function by some F in the family. So it's just usually, because the L function I'm used to are modular forms, so that's the F of a modular form. But so that's, imagine it's a chi, or imagine it's a t, whatever you prefer. And then the conductor, I will say that in my family, I want the conductor to be of size q, where the wiggly sign also means whatever you want. Say, for example, between, so it could be an equal sign, or it could be between q and 2q, for example, or it could be just up to q. I just need this family to be infinite when q goes to infinity. So maybe equal q is enough, but not always. So yeah, of size approximatively q is what I mean by this wiggly sign. And then over this family, we're going to study, I'm always clicking on the right button. Okay, let me start again. This one. Over this family, I'm going to study the average rank. So sum over order vanishing at 1/2 of the L function. Okay, and as analytic number theorists, we like writing ones or numbers as sums. So I'm going to write that the order of vanishing at 1/2 of the L function is the sum over the zeros of the L function, L 1/2 plus I gamma F equal to 0 of indicator of 0 of gamma, right? So this is the usual trick in number theory. When you have a quantity, you write it as a sum, sum of ones. And as I said, the correct normalization is with the log of the conductor. So I'm going to write log of the conductor here. I hope I'm writing the normalization in the right direction, yes. And where my C is the conductor, and since, yeah, so approximatively Q. Log CF. Okay, I'm writing the 0 at 1/2 plus I gamma. Maybe my hypothesis is false and this gamma is not a real number. Whatever, we are going to assume very fast that my hypothesis is true. So let's say I'm summing over real numbers in this talk. Yeah, and then the next thing we do when we are doing analytic number theory is we don't like step functions. So I'm going to replace this one by a smooth weight, which I would like it to be the closest possible to like this indicator of 0, but that's where where the things become difficult. So yeah, so no phi is, like, imagine it's the indicator of 0, but in a smooth version of it. So that it's getting like or if I'm back to trying to count in the interval, then my phi would be the step function that is 1 in the interval minus 20, 20, and 0. Otherwise, smooth version of that would be good enough. Then that would answer my first question about counting in the box. Yeah. So yeah, and then I average over the family, and this is what we define, what we call the one-level density for the family. And yeah, and then I changed just the log, the C into a Q because, well, this is a log of something, and I said C is close to Q, and well, when you do log, anyway, it's a constant function. So that's basically the same thing to do C or Q in this. And things are going to be way more simpler if I put a Q instead of a C. If I wanted to look at secondary term, it would be kind of questionable to do that. But today we're only looking at main terms, so that's good enough in my opinion. OK, questions so far? OK, so that's my object of studies, and that's the way we study low-lying zeros. And the stories is when you look at those quantities as q go to infinity, it appears that there is only 5 possibilities of what this limit tends to. And that was conjectured by Katz and Sonak following computation and IDs from Tyson, Montgomery, and Odliscu, and others who were interested in that. And by this discussion, that it seems that it started by this observation that it seems that the zeros of data are distributed a bit like eigenvalues of matrices in some random set. So this is why the conjecture is that there is the limit of the distribution of the zero will look like the limit of the distribution of eigenvalues of matrices in one of the possible random matrix groups. And so there's 5 of them that can be the correct one, and depending on what is the symmetry type of the family, which is what we call those matrix group, we have 5 different possibilities. So yeah, so that's what Scott Sonak are saying. For each time I put even Schwartz function, so my phi, the limit is going to be the limit of the integral of phi against some distribution function that is telling you, oh, the zeros are distributed against this phi. And I'm just writing here exactly the same thing. So this is Fourier transform side by Plancherel formula, because usually all the proofs that I've seen towards this conjecture are arriving through the Fourier transform side. So usually what we are going to prove is that the limit is the integral of phi hat against the w hat. So that's just why I'm writing. And so this is my definition of Fourier transform. So the same as yesterday with the 2 pi on top. Yeah, the question on that? Continue. So here I just put a picture of the possible symmetry types that, yeah, so as I said, there are names of matrix groups, so orthogonal, special orthogonal even, special orthogonal odd, and symplectic. And this is what the W look like, so depending on what is the symmetry type. And so you have to imagine that these are what the histograms of the zeros in the family look like when you take a lot of L function. So I'm going to, well, what do I do in histogram? I'm going to choose a little interval and count on how many zeros there are in this interval in my family of L function. And if I go 1, 1 each time, then this is what the histogram are going to look like. That's what the conjecture is saying. So in particular, say if we think that the symmetry type is orthogonal, it means that we think the zeros are basically very well distributed on the real line. Or if the symmetry type is special orthogonal even, then there is zero chance to have a zero exactly at 1/2, but there is a big chance to have a zero very close to 1/2, very close in the sense of the log conductor close. And while if I'm a so odd family, then there is definitely 1 chance over 1 to have a zero at 1/2, but then the next one, and the zero should be of multiplicity 1. Oops, sorry. And then the next one should be a bit further away, like it's repulsed from, pushed away from 1/2. And while it's symplectic, then there is no zero at 1/2, or zero chance to have a zero at 1/2, and still there is this repulsion happening. Yeah, other question on these graphs? Yes?
Are there more symmetry types, or is that all the ones there?
Yeah, exactly. So I said 5 and I'm showing 4. So yeah, so you should complain about that. So I don't have enough space to show 5 like this. Slides are too small, or this paper later is too small, or whatever. Yeah, so there is actually 5 symmetry type, and I'm showing 4 because the 5th one is unitary, and it's a bit boring, but it's I decided not to show unitary because it's usually for L functions that are not real. So, and I'm writing so that's why I wrote real families here. So for example, the L function are not going to be their own symmetric or their own, and so for example, if I'm looking at the family of all characters, then the type is going to be unitary. But if I'm going to look at quadratic character, then I'm back into real family, and that's one of those types. So and all the family I'm looking at are real, so that's why I'm writing only those 4. And one other thing we could argue is that the orthogonal family might not deserve to be called a family because it's usually just a split between, you can usually split orthogonal between special orthogonal even and special orthogonal odd. And if you can observe, maybe if you add those two, then and make 1/2 of this plus 1/2 of this is this one. And you can add the graph a bit, and you will see that they compensate exactly to have this one. So yeah, I could have removed the orthogonal and put the unitary, but that's, yeah. Yes?
You said that unitary appears when you have L functions which are non-self-dual.
Yeah.
Does that mean that any family which contains non-self-dual L functions will immediately be unitary?
That's what I think, but I'm not sure it's true. So I never studied non-real L function, but my first idea would be that, yeah. But yeah, if someone knows better, I don't want to. I'm possibly wrong, so I don't want to be sure about this. Okay. So I just put the Fourier transform side. So that's the same graph, except that the graphs are of W at instead of W. And so I'm saying exactly the same thing on this slide. And I just put this slide to show that in those 3 types, symmetry type, there is something funny happening at 1 or -1 in the W at graph. So there is this discontinuity that usually makes it hard to prove something around 1. Say, usually there is some more step if you want to prove something around this continuity point, which I'm not breaking today. So that's it. Yeah. This brings some more difficulty usually. So that's yeah, just this. Okay. Because the kind of theorem that are proved towards the Katsana conjecture are usually stuff saying if phi is an even-Schwartz function with support of phi hat in some symmetric interval minus sigma sigma, then then we have the limit as predicted by Katsanak. So so this one level density, sum over the f, sum over the zeros of phi log q over 2 pi okay, over the size of the family is supposed to tend to something. That's what we prove. So the kind of result is if support of phi hat, so as I said, usually we prove something on the Fourier transform side. And so there is a bunch of results. I did not write at all of the results in this direction, but there is this very fine result of Drapopart and Radziwill that is kind of recent, where they beat support 2, which was an impressive result for the family of all characters. So this is unitary. And for the family of quadratic characters, so here you need to range the conductor between, say, Q and 2Q, or even up to Q, I don't remember. And they have support 2. And so you see the kind of, I did not write all the kind of possible support, but there is some where it's sort of possible to get up to 2, and then it is difficult to pass 2. And sometimes it's possible to get up to 1, and then it's difficult to pass 1. Usually, the larger the family is, the easier it is to have big, like, because you're making a larger average, then you can have a better result. Yeah, so I'm listing the kind of L function that are related to the question of my talk today. So Dirichlet character, Eka characters, elliptic curves, modular form L function. And so all of these results are assuming or not Riemann hypothesis, or like say standard conjecture. And then there is under some other conjectures, like the ratios conjecture of Conway, Farmer, Zimbauer, there are other kind of results saying, like, well, under this conjecture you prove you have you have any support or stuff like that are and you can describe precisely the lower order terms and stuff like that. Yeah. So I think I'm not going to read all the names in these slides. I'm very sorry if I forgot yours. Yes? Okay, sorry.
One where the elliptic curve had a complex multiplication, where the elliptic curve doesn't.
Yeah.
So in terms of GL2, automorphic representations, you have one case which is dihedral, one case which is not, which will translate into a condition of the corresponding symmetric square. Do those correspond to different symmetry types?
I think if you're looking at the whole family of elliptic curves,
with complex multiplication or without, is there a dichotomy in terms of the symmetry?
let me think a bit, not to say something. Well, there is something, yeah.
Would you expect the same behavior if you were to take a sum over L functions, like what is vanishing for L functions of elliptic curves without complex multiplication, versus a family where they all did have complex multiplication? Do you expect the symmetry types to be the same?
Yeah, I think they're not. I I forgot the precise result, but I think they're not. I think there's, well, so,
One of
yeah.
them is like is the CM case orthogonal and
Is it that?
CM case, like,
Yeah, symplectic or something.
Yeah.
I think it is. Yeah, I should check this, but yeah, there's, well, so yeah, you need to have the family, and there is a precise definition of what a family needs to be, but yeah.
behavior to be really different.
Yeah,
I don't know whether or not.
I think they're, yeah.
Thanks.
And that's a good question. I need to check that again. But I think it is, yeah. So, yeah. But I think, like, for example, Isbron already is doing the 2 case, and I think it's doing the largest family possible of all elliptic curve, and then you don't see the CM ones because they're too small, and that's, you get a symmetry type, and then it's doing a special twist of one CM elliptic curve as one family, and then it gets something. So, yeah. I'll read this paper at the break. Okay, and so to come back to my initial question, which was what I wanted was the average rank of the family, then the thing is, if you're able to prove the Katsana conjecture for a certain support, say for phi at between supported between minus sigma and sigma, then you can choose whatever you put for phi at, say something, for phi, say something that has positive value, and then I can say that the average rank is going to be smaller than this, right? 1 over fq, sum over f of order at 1/2 is going to be smaller if this is, say, if this is 1 at 0 and positive otherwise. So for example, this function, this sine square, is satisfying this thing. So sine square looks like that, right? So that's my good approximation of my indicator function of 0. And that's nice because, well, the reason why we're taking this one is that the Fourier transform is kind of easy, right? It's the tan function between minus sigma and sigma. And then if you plug that in the limit, then it's easy to compute the integral against the w at. And so that's giving you an upper bound on the average rank. So for example, in the case SO even or SO odd or orthogonal, if I don't get past support 1, they all look the same. I don't know if you looked at that. They all look the same between -1 and 1. They are orthogonal families. So the integral is going to be the same. And so I get a bound on the average ring, which is 1/2 plus 1 over sigma, where sigma is the best support I can get. And in the symplectic case, we get a better bound on the average ring, because there is no vanishing at 1/2 for the symplectic case. Okay, so yeah, the better the support we have, the better bound on the average rank, because same, like I wanted my 2 put phi to be the indicator of 0, and the Fourier transform of this is flat is equal to 1, and that's exactly not the kind of thing that has compact support, but the best approximation I can have to that is something like that for now. Yeah. And so, yeah, if I want to have a good bound on the average rank, say if I want, so the best I can have for the bound of the average rank is getting support up to 1 would be rank 3/2 for the orthogonal families, right? And so if you can prove that the average rank is small, say, for example, you know that your average rank is 3/2, then there is definitely not too many L functions that have big rank. So not too many L functions that have, so there is, like, well, the dream would be, if I can prove that my average rank is 1/2, say, then I know that there is a lot of L functions that have rank 0. So no vanishing at 1/2. As we expect that L functions do not vanish at 1/2 except if they have a good reason to. So, so that's the kind of result we hope to get by doing all of this thing, is proving that there is most of the L functions do not vanish when they are not supposed to vanish. And if they are vanishing, then they should be vanishing only with multiplicity 1. And so that's what we say. So maybe I had written something not in this thing. Yeah, so if you get that the average rank is more than 1, then you deduce positive proportion of rank 0. And you can do a bit smarter than that if you separate according to the sign of the functional equations. That's why my SO even and my SO odd are in different lines, because usually the SO even L function will have it will have sign of the functional equation is equal to 1. So a priori, there is no reason to vanish at 1/2. So if I know, and then it implies that the order of vanishing at 1/2 should be even. So if I know this, if I'm summing over a family where I know this is even, then I just need to know that this average is smaller than 2 to know that there is a positive proportion of non-vanishing. So that's, we get this, that the proportion of non-vanishing for the SO even case is going to be this 3/4 minus 1/2 sigma. And in the symplectic case, it's always better because of this repulsion of zeros. And while in the SO case, usually you will have a sign of the functional equation that is negative, so you will know that there is a 0 at 1/2. And so there is a 0 at 1/2, but we want to prove that there is no more than 1 0, so multiplicity 1 of the zeros. And then that's the proportion you can get depending on the support. So, yeah. Okay, and now we want to go back to the page of result that I showed you with what the support they have, and get to know what are the proportion of non-vanishing they obtain. But instead, I'm going to talk about my result and show you what are the thing we got. Other questions on that? Or do I continue? Okay, so the family I was interested in, or we were interested in with my co-author, is, so I'm looking at this elliptic curve, which is defined by, which the way I understand elliptic curve is it's an equation. And so this one, y squared is equal to x cubed minus x. And then we do quadratic twists of this elliptic curve. So I'm just putting a d in the equation here. So what I mean by quadratic twist is that this elliptic curves are the same, or have, there is a bijection between the rational points in fields where quadratic root of d exists. Okay, because I can make the change of variable to if I have a quadratic root of d, I can even show you because I'm very proud I found it. So, because d to the 3/4 y squared is equal to d to the 1 of x cubed minus d times d to the 1 of x. So if I make the change of variable, and this is d to the 3 of times y x cubed minus x. So if I make the change of variable xy becomes d to the 3 of, d to the 1 of x, d to the 3/4 y. I change between the two, I make the change of, this change of variable makes the bijection between the points, the rational points of one curve to the other. And I need the d to the 3/4 to exist in my field to have this change of variable being on rational points. So this, this elliptic curves interested us for some reason, and I'm going to explain to you later. And then, well, to this elliptic curve, you reduce that modulo primes, and you count their number of points in a FP, and the usual result is that this number of points is close to p plus 1 up to some AP of E, so up to some value that we call AP that is about of size square root of P. So we normalize it by square root of P, and then it is something smaller than 2, so we write it as 2 cosine of some angle. And it happens that because it is a CM elliptic curves, that it can be written as this angle can be encoded by a Echo character, and this one is defined over Zi. And if you don't know Echo character, you can imagine it's a version of Dirichlet character that is defined on just Zi instead of Z. And the difference with Dirichlet character is that it can be of infinite, it does not have to have a finite order. So this one, for example, is really sort of, so the side that I wrote here is really giving you the angle of the primes or of the point. And if I choose the correct representant of my ideal, and the correct representant has to be the one that is 1 modulo 2 plus 2i. So that's very technical, and that does not matter much. The thing is, the number of points of this elliptic curve can be encoded by this character, which has infinite order. Let's keep to that. And with this setting, and then there is a quadratic symbols, which this one is something like that really looks like a Dirichlet character, finite order, that is telling you if something is a force power or not modulo P. So the same generalization of Legendre symbol. Okay, I'm going too far. Okay, back. Okay, and so with this setting, we were interested in 2 different families, and you can discuss which one is more interesting to you. I was more interested in the first one, so this is the one we worked with first, and then, well, so people who are interested in elliptic curve will say that the second one is more interesting, so that's why we studied this one also. So, so the second one is looking at the L function of the elliptic curve, and varying the D, so varying the twist of the elliptic curve, and so that's a family of CM elliptic curve. And the first function is looking at powers of my character, psi D which, okay, I did not write what is psi d. Well, say this is psi d of p. So psi times the quadratic symbol is psi d of p. And since psi d have infinite order, I can take all the powers of this character, and that's going to be different characters all the time. And that was a family that I was interested in because it's what is coming after? Yeah. Because it's, so in particular, in the case d is equal to -1, this family of powers of character, as I said, it's talking about angles of Gaussian primes or something like that. And that helps me to study this function, the question of looking at, so if you write a prime as a sum of two squares, so this is a prime that is congruent to 1 modulo 4. I write it as a sum of two squares. There is necessarily an even square and an odd square, so I'm writing a 4 here to differentiate the even and the odd. And assume that the odd pod comes from a like positive number, then the question is this number A congruent to 1 or 3 modulo 4? And can I compare those two? Is there more chances that it is 1 or 3 modulo 4? So that's a question that I was asked related to Chebyshev bias, which is a completely different topic from today, but I want to make an advertisement for that. So that's just like if you already heard of Chebyshev bias, you might understand what I'm saying. If not, it's just some question about distribution of primes, and I just wanted to look at this if A is A 1 or 3 modulo 4. And so the distribution of this, the question is related to this angle where for that, the distribution of the APs for D is equal to -1. And really what is related, as you know, stuff like zeros of L function are related to distribution of primes. So zeros of the L function of those powers are giving me all the information I need to understand the distribution of this, the question on this distribution of primes. And so in particular, I was interested in the vanishing at 1/2 for this L function, and I found out that, well, it is a bit weird because I computed the sign of the functional equation for this L function, and I found that the sign of the functional equation is 1 if the power is even, or 1 modulo 4, and it's -1 if the power is 3 modulo 4. And in more general, with Lucile Devin and Ezra Waxman, we computed that for all D, if you look at the L function in the family of powers of psi D, there is 1/4 of the L function that have negative sign of the functional equation. And it is kind of weird because usually in families, you would have 1/2 or 0, but not 1/4 of the L function that have vanishing at 1/2, say. So that's why we got interested in this family. And okay, so then I'm just going to show you what this implies. So when because of this result, I was able to heuristically explain why this graph is always positive. So this is my Chebyshev race, which I call Fourier's bias because it was a question of Fourier, where I count how many primes lower than x have the A that is 1 modulo 4 or have the A that is 3 modulo 4. Yes?
So in the previous theorem with Waxman, what do you assume?
And this one?
You assume unconditional.
This one we computed the root numbers. So yeah, there is nothing. So yeah, and so but to explain why this is not changing sign, I'm assuming a lot, and in particular, I'm assuming that if the sign of the functional equation is exactly giving me the order vanishing. so that if the order if the sign of the functional equation is positive, then no vanishing at 1/2, and if the sign of the functional equation is negative, then vanishing at 1/2 of order 1. And then, well, you see that it does not change sign, but the explanation I have to explain why it does not change sign is highly heuristical, see. And so, yeah, so that was sort of the first bias that I found that is completely in one direction and without, there is more bias that are complete, but this one I was very happy to find. So that's some advertisements for this other result of mine, and I'm just showing this slide to make you want to read my other paper. And so yeah, you see this is clearly growing to infinity, right? It's up to 8, as 8 is infinity. So yeah, I'm not staying too long on this because that was another subject, but I think it's interesting. And so since this family has the signs that are kind of weirdly distributed, we discovered that the correct way to study this family is to separate according to sign of the functional equation. And the good way is to look at the powers modulo 8, contrary to what I have in the previous slide where I was looking at congruence classes, congruence class modulo 4 of the power. In D is equal to 1, you need to look at congruence class modulo 8 to separate the signs. So, so we separate according to classes modulo 8, and then what we obtain is that in the family, the one-level density associated to this family of powers in some class modulo 8 are of symplectic type if the power is even, and it is of orthogonal type if the power is odd. And we prove that with support between -1 and 1. So we don't see the difference between the 3 orthogonal types. So that's why I'm just writing orthogonal type here. I'm expecting that in the case alpha is odd, then there is actually 2 cases. There is the case where alpha is odd and the sign of the functional equation is negative, which I'm expecting would give SO odd. And if alpha is odd and the sign of the functional equation is positive, then I'm expecting it will be SO even. But we don't see it because we cannot pass support -1, 1. As I said, that's exactly where the difficult part is where we should see the difference. And that's, yes?
Really striking result. Are there analogs of this type of result if you take a sum over all elliptic curves with complex multiplication, maybe ring class twists with a given sign? Are there other results in this direction, or is this?
I think this is a
general case.
Well, so this is not CM elliptic curves, right? I'm just looking at one CM elliptic curve and powers of the characters. So that's.
Yeah, but I'm asking a question about is there a larger family of elliptic curves with CM?
I don't know. This was a family we studied because I was interested in for the other reason, and that's the first time I see that. Yeah. So yeah, I think that's why I'm kind of proud of this result, and yes. So yeah, maybe I'm not going to spend too much longer on this, and then I can show you that. So from this, as I told you, we can deduce. Since we get support up to 1, we can deduce the vanishing proportion of non-vanishing. So like in the family where the alpha are even, then we get that there is 3/4 of L functions that are not vanishing. And like the result, as I showed you with the formula with the sigma earlier, that's exactly that with the putting the 10th function in the computation. And just to finish, this is the advertisement for the result to come on the other family of quadratic twist of my L function. And for this one, for now we have support minus 1/2, 1/2, but we are still working on that. That's why there is a star here. And Alessandro Fazzari joined the team. And so yeah, we hope to get better. But for now, the result is with 1/2. And maybe next year, if I can't get to come again, I will have a better result. And so that's what symplectic family. What do I have? Yeah, orthogonal family. Sorry. So that's an orthogonal family, and we don't see the difference again since its support. The support is kind of small, and so that's the best result we can have is a bound on the average ring that is still a bit bigger than 2, so we don't have non-vanishing results yet. So yeah, thank you for listening and for all your questions.